Hello everyone, welcome back to the channel. In this particular video, we will be covering the Verilog module. We'll be starting with Verilog module. In this video, I'll be covering the basic understanding of Verilog language, what language is and all. So before starting this course, it's better for you to have the prerequisites, that is, you have to have a basic knowledge of digital electronics, and if you have any knowledge of any programming language, that is preferred. It will help you a lot in the course. If you are not, then don't worry, we'll cover all the concepts on the go and I'll make it easy for you to understand this. Then we'll learn the concepts of Verilog language in this course. We'll see the constructs, keywords and operators. We'll see the guidelines for synthesis. What synthesis is, I will explain you in the upcoming slides. We'll perform a coding of combinational, sequential and FSM blocks. Combinational circuits will design, sequential circuits we will design, and we'll also design some FSM blocks. Test bench coding will do. We will design our own test bench using Verilog. Then simulation and synthesis will do using open source and free tools available over the internet. What simulation and synthesis is, you will get to know in upcoming slides. So what actually Verilog is? Verilog is a HDL language. HDL, when we say, that means hardware description language. As the word says, what this language will do is it will describe hardware. That means if you have some digital circuit like this, if you have any, you will be describing this circuit in language form, right? So this is Verilog. This is a high level computer language. When we say high level, that means it has keywords similar to English language. This language can model, represent and simulate digital design. So this is basically what we are doing, is we are performing this digital design into using coding. We are doing that. This language describes the behavior and structure of the digital circuits, and as I said, this is a textual representation of digital logic design. So how Verilog was actually came into the picture is, in 1984, Gateway Simulation, this was a company who created Verilog as a proprietary tool for their internal purposes, right? Then what happened is they started using it and they find out the benefits of this language as a tool. Then in 1990s, Gateway Simulation was acquired by Cadence, and in 2001, IEEE was standardized. The syntax of Verilog language was standardized by IEEE. So IEEE has given the standardization for this particular language. So over here, this is the Verilog version we are using as of now. Then in 2009, what happens is System Verilog language was made out of Verilog, and it is also standardized by IEEE in 2009. So System Verilog is also on the backend is based on Verilog. So this Verilog version we are using, and this System Verilog we are using as of now in the industry. So the application of Verilog over here is, as of now you might have understood, to design digital circuits, but actually how? So what happens is, on the backend, for example, let us say we have a digital system. When I say digital system, we can have your PCs, your laptops. We have this laptop will be containing a motherboard or a PCB board. What will happen is this laptop will be working based on combination of two things, that is hardware and software. So in software, what happens is you design the softwares, you have the OS, you have the utility softwares. For example, whatever the softwares are responsible to make a environment run and to make it up for you. Next, in hardware, what happens is, on this motherboard there might be different ICs which are connecting and working together to perform a specific task. So these ICs are being made, so these are actually ASIC ICs. ASIC means application specific integrated circuit. If you want to see actually what is the difference between ASIC, FPGA, PLD, I have covered it in previous one more video. I'll provide the link over here, you can watch that video. So these all are ASIC ICs. So these ICs are being designed using Verilog language, and then similar, these ICs are being designed and these are put it onto digital boards. So on digital boards, so the software is applied, the software is being installed on this motherboard, then these ASIC ICs are being installed. So this combination of them both makes this digital system work. Next, this is a very important slide. When we say synthesis, what actually we mean, and when we say simulation, what actually we mean. So when we say synthesis means using Verilog we'll be writing a piece of code to describe a digital circuit. So what happens is, this is a .verilog file, that is .v file. So what will happen is, using the tools available in the market, using EDA tools, what will happen is this will be converted internally into digital logic. How actually this design will come into existence, right? This will see, for example, let us say any circuit is there that we will see. So how this code, the turning of this textual representation into this gate level representation. So this gate level representation is called as gate level netlist. So whenever the RTL code, when I say RTL code, is means this .v code, this textual representation is being converted into this gate level representation. We will, what we call is a gate level netlist. This process is called synthesis. Okay, now what happened is, we have got this design, or you have written a code. Now you want to verify your design. So you have your design. So in this design, for example, let us say for 4:1 marks you have designed, and you want to check it. So whatever the inputs you will be applying, and you will be checking the output, this process, the process of applying the inputs and checking the outputs, checking the waveforms at the output, this is called simulation. So in Verilog language, it provides us keywords. Some of the keywords are synthesizable, means when you will be using those keywords can be converted from textual format to the gate level representation. But some of the keywords will be there which can't be converted to this gate level design, right? So Verilog includes these type of both the keywords or constructs, we will say. So some of the constructs are there which are being included in this particular language, which are not able to convert into the gate level netlist, is only because for simulation purposes, that you can design your test bench in Verilog also, and you can provide the inputs and outputs, and you can check your circuit. So that's why Verilog consists of synthesizable constructs, simulation constructs, and some of the constructs are there which are both synthesizable and simulation, used for synthesis and simulation both. So this thing will get it more clear to you when you will start coding. So there are different abstraction levels Verilog provides us. When we say abstraction levels, means different stages or different levels which you can touch using the coding itself. So using coding you can design directly at a circuit level. When we say at circuit levels, you might be writing some keywords like CMOS. You will be providing the inputs of this CMOS, what should be the input, what should be the output, like this you will be coding. So directly you will be coding at a transistor level, so that we call circuit level. Gate level, when we say, in gate level coding, what you will be doing is you will be writing the keywords like not, and, or, the inputs, outputs, all that. So this type of coding, when we use, we say it as we are performing the design, or we are using the gate level abstraction level, right? So moving ahead, what another abstraction level Verilog supports is data flow level. In data flow level, what happens is you just simply need to provide the expression. Instead of writing the gates directly, for example, over here you were writing the transistors, these transistors will make gates, these gates will make logic, and this logic will make another circuit work, right? So in this case, we have directly moved to gates. Now further ahead, in data flow level, what will happen is, in data flow level, we will be simply writing the expression, for example written over here. You'll simply write y equal to a and b or c. Internally, Verilog will interpret this, and it will automatically design this circuit on the backend. You no need to worry about AND gate or gate. You no need to worry about it. Will be taken care by Verilog itself. Now the next, this is data flow level. Next, this is the most important one, behavioral level modeling, which is being used currently in the industry. Currently this behavioral level modeling is the one which is being used. In this, what happens is you simply define the behavior of the circuit you want to draw. For example, if you want to draw a 2 into 1 mux, this mux will be containing different AND gates, OR gates, their connections, everything else. So you no need to worry about that. What you will say is, my logic will have two inputs, one input A, one input B, and will have one output Y, and it will have one input as select line S. If select is equal to 0, I need my A to be available at output, else I need my B to be available at output. So you have simply defined what over here is only the behavior. You have defined only the behavior of the circuit, and internally what gates will be required, how the connections will be made, what will be the connections between input and output, all this will be taken care by the language. So these are different type of abstraction levels which are being used in the Verilog language. So this you have to keep in mind, because sometimes you might be using the combination of two at once. You might be using the expression also, and you might be using the behavior also. So the thing is, why abstraction levels are actually required for us. Before explaining this, I'll explain you that whenever there is a design made in Verilog, how it is being made. At first what we do is we make some sub modules. Okay, so whenever we write a code in Verilog, how we design it, at first we create smaller sub modules. We create, this one will perform task 1, this one will perform task 2, this will perform task 3. Then we combine these 3 to make one more bigger logic which will perform a bigger task, big task 1. Similar, then we make the actual system. So this is how we break the hierarchy in Verilog. It can be bottom to top or top to bottom based on the IPs we are using. So what is the use of this is, it increases the reusability. Any company, any chip, or any IP, or any IC, I would say, which require this functionality, they'll import this functionality directly. Some might require this, they will import this. Some might require this, they will import this. So there is no need to again and again write the code of this. Once you have written, you can utilize it. So that is the benefit of breaking down in modules. So now moving ahead, so why abstraction levels are actually required, why we are differentiating between transistor levels, the gate level, and the data flow level and the behavioral level. What happens is some company might be operating on the system levels. For example, well, let us say we have the motherboards directly, we have the ICs. So some of the companies are there which are interested in directly importing these ICs and making directly their boards. So over here, for example, Samsung, Apple, these companies are operating at system level. So what they do is they directly import this and they directly integrate this. So over here they use the language for their at a system level. Then what comes next is internally in this motherboard, each IC will be having some registers in it, some internal modules. Now let us say this particular module you want to import from somewhere else, and these three you will be writing at your own. So over here you want to have a register level, abstraction level, where you will be importing this, writing three other modules to make an IC. So over here, to at this particular level, this this simpler module structure, the abstraction level of register level is used. Next comes is gate level. For example, the EDA tool companies which are doing what is, they are simulating the design, they are synthesizing the design. So based on some code they are changing it into gate level. So when we are changing it onto the gate level, they might be having the information about how this code should be converted into gate level. So that's why they needed this gate level abstraction. Next we move to transistor level. When we say transistor level, the companies want to make a logic directly using the transistors. They want to change the technology, they want to upgrade the technology, or they want to launch some new tech, their new innovation. So the companies, for example, Apple also uses this, IBM, all these companies use transistor level to launch their next generation software, next generation hardwares, next generation ICs. So they directly work on transistor level and they do use this transistor level, abstraction level. Alright, so that's why this all different levels are required in language, where you can directly code, where you can touch the level, where you can touch a gate level, where you can touch transistors, where you can touch registers, or where you can have a complete IC level uh, coding. Next what we have is why how Verilog is different from other programming languages. So what happens is, exactly understand it very clearly, this is very important. So what happens in other programming languages is, let us say I have a piece of code, line number 1 2 3 4 5 6 7. So in other programming languages what happens is, when you are it starts from over here and it second, then it goes to, so what happens in traditional programming languages is, it starts from line number 1, it goes to line number 2, then it comes to line number 3, then 4, then 5, then 6. This is how it executes the program. So this is a sequential flow. But in case of Verilog, the things are different. Over here how it happens is, there is a code which you have written in Verilog. This code, this is the code, main code. This code might be containing some different subcodes. In these subcodes different lines are written. So what might happen is, these codes will be executing in parallel and the internal code in them will be executing sequentially. So that's the beauty of Verilog. It also executes parallelly and internally also executing sequentially at the same time. So the timing constraints are also there in this language, which are mimicked, which are not there. The delays and everything else is not there in the traditional programming languages. So why this functionality is required, that sequentially and parallelly, is because in digital circuits what happens is, if we are having a digital circuit, it is having one input, outputs, and there are some modules which are internally working. So let us say the output of this module is an input to this module, and the output to this module is input to this module, and but this input is also input to this module. So what happens is, this module is dependent on this module also and on this input also. So what will happen is, these two blocks should work parallelly, so that it can provide the input to this, and the main input can also reach to this. So that's why some of the blocks, for example, let us say this block is having a dependency, so this block might be working, these two blocks might be working in parallel to make this block work. For example, let us say the output of this block is an input to this, and the output of this block is also an input to this block. So this block will only work when it receives input from this block and from this block also, right? So these two blocks, block number 1 and block number 2, should work in parallel to make block number 3 execute. So this is how Verilog language performs its execution. The structure hierarchy in Verilog I have explained you. So coming next, what we will be learning is, we will be starting with the keywords in Verilog. Then we will be moving to the modules in Verilog. This one is very important because everything in Verilog is being done or encapsulated in a module. Then we will be moving to the data types in Verilog, and then we'll be moving ahead with the basic coding of some small examples. We'll start with coding of half adder. We'll make a half adder, then we'll make a full adder using half adder and or simply a full adder. All right, so great things are coming up. It was going to be very interesting. Be connected, keep going, keep learning. Thank you.